Consider if we have a differential equation, first order equation, y prime equals f of ty, where f of ty is just any function of t and y, along with an initial condition y of t naught equals y naught. Now there's no guarantee that we're going to be able to solve this equation, but whether we can solve it or not, we assume that our function f of ty is one that we can evaluate for any value of t and y. That means that we can specify a slope field down here. We could evaluate f at a variety of points t and y, forming a grid and sketch in slope segments, and we've seen that. And we could certainly do that, but right now we're going to just try to trace a solution curve, or an approximate solution curve, through the point t naught y naught in the y versus t plane. So here we have the point t naught y naught. We can evaluate this function, and the value of this function is going to be the derivative of our y function, our y versus t function, so that this function is going to give us the slope. So we have a slope f of t naught y naught, and that slope might go on for a while. Now we consider what happens if we follow that slope for distance h. We can form a right triangle with horizontal leg h and a vertical leg, which we'll designate by delta y. And we ask, what is delta y? Well, delta y, as we well know, is simply, since the slope is rise over run, which is delta y over h, delta y is just the slope, which is f of t naught y naught, multiplied by h. That's slope times run. So our t-coordinate changes by h, our y-coordinate changes by delta y, giving us a new point, which is t naught plus h, y naught, and this thing's getting in my way here. I think we can get rid of it now. Y naught plus f of t naught y naught times h. Now that's not an exact point on our graph, because presumably there's no reason to assume that this function is going to be the same at every point along this line, which means that the slope of the actual graph is actually going to be changing as we move from here to here. But if this is a small distance, then this will stand to be a half-decent approximation, and we can quantify how good the approximation is likely to be, but let's just worry about the process for right now. Now I'm going to call that point T1, Y1, so that we can say that T1 equals T naught plus H, and Y1 equals Y naught plus F of T naught Y naught times H. Okay, having gotten to this point, we can find a new point based on the slope at this point. So at this point, let's say we have a new slope. And let's make that new slope a little steeper, and let's label that okay. Well, we have a new slope, which is f of T1 Y1. Having obtained T1 and Y1, we can follow this new slope for a distance h and get a T2 Y2. If we do that, we're going to see that, well, T2 is T1 plus H, if we move over distance H, and I haven't indicated that on the graph, which is complicated enough now. Or not complicated, but crowded enough. T2 is T1 plus H, and what's Y2 going to be? Well, if we complete this triangle, come over H and up a new delta Y, we're going to see that Y2 is equal to Y1, which is the coordinate of this point, plus what? The product of the slope and H. The rise equals the run times H. So it's going to be Y2 equals Y1 plus the rise. The rise is F of T1 X1 multiplied by H. In general, we're going to be able to keep iterating this process. We simply have evaluated our function at the point we found, T1 X1, to get the slope that we use to project forward to the next point. And if we continue doing this, we're going to see that in general we get Tn plus 1 equals T sub n plus H, and Yn plus 1 equals Yn plus F evaluated at the previous point was the point Tn Yn times H. And I wrote this as X, and I have no idea why I did that. But let's make sure we understand that's a Y. So this is X of T sub n, Y sub n, where T sub n, Y sub n is the last point that we got, and n is whatever number. We can get, if n equals 1, we see, for example, that Tn Yn is T1 Y1, and Yn is Y1, and Yn plus 1 is Y2, Tn plus 1 is T2, Tn again is T1, so that for n equals 1, this equation is just an instance of this. So that we can proceed through a number of steps. We can find T3, Y3, T4, Y4. If n is equal to 10, we'll eventually get to T11 and Y11. And we can continue this as long as we wish. Now, every time we make a new approximation, we're going to be subject to some error because the slope doesn't remain the same between here and here, and by drawing this as a straight line and assuming that this slope holds throughout this interval, we've made some sort of mistake in finding this point, and that's going to be compounded when we find the next point and the next. So if we go too far, our solutions are going to become unreliable. We call this process Euler's method, and basically all we need to apply Euler's method is the function f of ty, which is a known function and a function that's well behaved over at least some region, over the region in which we're approximating, and t naught y naught, a value of y at a given value of t, and that's given. Then the method just says that t sub n plus 1 equals t sub n plus h, y sub n plus 1 equals y sub n plus f of t sub n, y sub n times h. And remember that t sub n, and I got to make my n's look more like n's and less like h's, tn y sub n is just the slope. H is your run between points. And I guess another thing that's given, we choose an appropriate value of h and we have to choose an h that's small enough that these accumulating errors are not too large. And then, having chosen that h, we can project as far forward as we choose, as far forward as we trust our approximation to be useful.